Bien, ce soir, nous avons le plaisir d'accueillir Caslav Brukner, qui est donc le directeur de l'Institut d'optique quantique et d'information quantique de Vienne, et qui va nous parler du sujet « Observer l'observateur ». Donc, Caslav, ça va être à toi.
Thank you, Hervé, for inviting me here. I decided to talk about, in a broader sense, the quantum measurement problem, and about things that I have been thinking for a while, for the last couple of years. It's somewhat scattered results in 3 different directions, and I'll go through each of them. But the basic idea is that quantum mechanics teaches us, of course, that we should put in question our notion of physical reality as we know it from classical physics and everyday experience. And maybe the prime example of that is certainly Bell's theorem, that roughly speaking can be interpreted as telling us that that the idea of particles carrying properties prior to and independent observations might not be true in quantum mechanics. Of course, we talk about here local properties of the systems. But nevertheless, we think that immediate experiences, for example, observation of events in the laboratory, like a click in a detector, photo detector, or maybe the spot on observation screen, these things we still think are objective in a very classical sense, and that we can define them for all observers at the same time, and we should not have problems with that. But now, when you think about the Wigner's-Friend situation, I will introduce it soon, then, and you believe in the validity of quantum mechanics to the domain that have not been tested yet, I should be careful here, then maybe you can create and derive no-go theorems, similar in spirit as Bell's theorem, which might put even these clicks in the detectors in immediate experiences into the question, as if we want to think about them as objective. And so that's the large part of my talk will be devoted exactly to this question. But as I said, I have several scattered results around the measurement problem, and here's the outlook of my talk. I will first introduce the way how I understand what the quantum measurement problem is. Then I will look at a possible path that, at least for me, is feasible and interesting and acceptable for towards the solution of what is the standard quantum measurement problem. And then I will move to the Wigner's-Friend thought experiment and to the no-go theorem that is now literature called as no-go theorem for observer-independent facts. And then, as a solution of this no-go theorem, I will discuss a possibility to think about facts relative to the observer. And finally, if time permits, I will also tell you how you can convince yourself that you are in a superposition as an observer. I thought that it's impossible a year ago, but I think now it's possible. Who knows what will be in a year's time. Okay, so here's the quantum measurement problem. We are all familiar with the fact that standard quantum theory actually describes 2 processes. One, the process which is related to the measurement. It's called technically quantum state reduction, sometimes wave function collapse, which occurs during the measurement or immediately after the measurement has been performed. And that there is a second dynamical process, which is a unitary evolution, which describes the transformation of the state in between measurements. And now, this is fine. I have no problem with this, that there are 2 possible dynamical processes, if I would really know when to apply which. Because the question arises, what makes a measurement, or when does a measurement take place? And these things are fuzzy, not well defined. And the way how I like even to dramatize this is that in the course of the quantum mechanics theoretical, you learn about these 2 processes, and it relatively well defined. You say whenever you perform the measurement, you apply the projection postulate, and whenever in between measurement, you apply unitary evolution. But then after finishing this theoretical course, you are sent to a lab, And then you see there are many different elements. This is a typical optical, quantum optical lab. There is fibers, I think here are somewhere maybe detectors, a lot of beam splitters and so on. And then you want, for example, to compute what will happen in this setup once you start to run and turn on the laser. But nothing in the theory tells you on which element you should apply unitary evolution and on which element you should apply projection postulate. There is nothing that tells you in advance. So it's only through the experience, maybe, after a while, that you may find out when to apply what. And so for me, still there is a question, which is a physical question, in my opinion, where should I apply a unitary and where state reduction? How can I know in advance that a piece of matter, like a photodetector, is a good device for detecting photons? On the other hand, I have a beam splitter, it's also a piece of matter or something. And when I think about the beam splitter, I realize that it cannot serve for detecting photons, but rather can apply certain unitary on the photons. And what is really funny for me, I'm sure that manufacturers of photodiodes really know the answer to this question, otherwise they would not be able to devise and sell photo counters. But physicists have not understood this yet. I think the way how the real feature that distinguish these two different devices have something to do with irreversibility, and I use here Bell's wording for all practical purposes, and I'm trying now to argue in favor of it. But in order to do so, I have to say something about the notion of classicality. So when you look at a detector, it's a classical object in very similar sense as this magnet. And when we look at a photodetector, we don't look at the really microscopic features of this. We are not interested in every single, maybe, atom sitting there, just like we are not interested in a magnet on every single atom that is zoomed in now. And this atom could actually decay, maybe, and turn into the orthogonal state. And then from the quantum mechanical point of view, I would say these two things are as orthogonal as they can be, because they are orthogonal quantum states. Nevertheless, we perceive it as the very same magnet. So similarly, when I look at a photo detector or detection device, I'm not really interested really in the distribution of any constituents of that, electrons or whatever. I just look if it clicks or it doesn't click. That's all what I'm interested in. So what I want to say is that when we think about detection, we think about some kind of a coarse-grained measurements, namely a very non-detailed picture of the device. And then we realize that it does click or it doesn't click. And here I also talk about coarse-grained measurements, and I tried somewhat through the analogy to the spins to also say something about the detection procedure. And a very long time ago, I was interested in a coarse-grained measurements on a spin system, and this is a very large spin that can, for example, point into certain direction, like here. And what we at the macroscopic level, at the level of everyday experience do, we actually perform coarse-grained measurement. And here I simulate, represent this with certain surface on a sphere, and I don't really distinguish better than this certain cap on the sphere. But maybe I can look at the other outcomes, but all what I do in coarse-grained measurements, I measure so-called POVM, positive valued measured operators, that are really coarse-grained patches of the phase space. Now, it turns out that for the spin, and similarly then people have extended this for other systems, is that if you are really interested just in the macroscopic properties of a certain system, for example, does spin show is directed in the north hemisphere or the south hemisphere is a very coarse-grained measurement, then you don't need really to look at the state, quantum state of the system, but you can look at something which quantum opticians very well known and call Q function. That's all what you need if you're interested really at the coarse-grained measurements. For example, when you look at the description of a spin system with a limited precision, namely that the uncertainty in measurement of the spin is much larger than square root of j. Square root of j is a typical uncertainty for a spin system. So if you're really very bad in your measurements, then you don't need to know quantum system. Quantum state, it's enough to have this Q function, and Q function is positive, it's a probability distribution, and everything can be described as coming from this well-defined positive probability distribution. In a sense, this can serve even as kind of a hidden variable for all macroscopic observations. And here is a typical example of a Q function for something which is a pure superposition of very large spins. If the spin is very, very, very large, you can think about that as a Schrödinger cat state. And here is just a mixture of these two. So we will see this is very quantum and this is very classical. But on the Q level, on the level of macroscopic state, the Q functions, the two functions are very, very similar. What does it mean? It means that we will not, under the coarse-grained measurement, we don't see the difference between something which is very quantum mechanical in front of you with no decoherence. I'm not talking about any dynamical process of a loss of a coherence. We have a pure quantum state in front of you, but we have a restricted means to read it out, and it looks like classical, just like that. There are small difference that on this size, and you won't see it actually. You have really to zoom in and see these small differences that will then correspond to the two Q functions. So the first lesson that I want now to tell you that if you have a coarse-grained measurements, you will not realize whether something is in a superpositions or it's a classical mixture. So even if you think about detection device in some pure sense, unitary sense, you want to describe this as people, for example, in supporting the many worlds will do that. If you apply coarse-grained measurements, if you are just interested if the detector clicks or doesn't click, you will not see the difference between that and a classical mixture. So at some point, when you start not to follow all degrees of freedom, the things will appear as if they are just in a classical mixture. Okay, that's one thing.
One question.
Yes?
You say that you don't mention decoherence, but in fact, using coarse graining is the same thing, because that means that you don't take into account many degrees of freedom. And either that comes from decoherence with the environment, or that comes from
I think they are compatible,
but the result is the same.
Are compatible, but there is some maybe flavor, more of epistemological flavor here that you don't think about, not necessarily think about any coupling and dynamical.
It's simple.
It's just like taking the measurement device and defining the precision, but at the end, one can be described with the other, and I think they are compatible.
Yeah.
Okay, now here is a measurement event. Like we have something coming to the photodiode, and we here click. That's what we do in the lab. Almost never, actually never. We see a reverse process in which the detector declick and send out the photon. Now, why it is so? So what I want to now argue is that if you combine coarse-grained observations, as well as certain and accept that you don't know fully or you don't have a full control over details of interaction, either among the constituents within the detector or with the environment, then such an irreversible, for all practical purposes, process is necessary happens. And in order to argue for that, there's a little bit of now mathematics here. I introduce a measure of macro irreversibility. And what is this? So this is a Q function of certain state, a pure state. And this is a Q function of certain state going forward and then backward. And the way how it's nice to illustrate this, you start with some state, you go forward with some H0 Hamiltonian, but then you say, I don't really control this Hamiltonian well, or I don't really know either initial state or this Hamiltonian, so I go backwards with something which is not quite H0, but H. And then, well, I end up somewhere else maybe, because these are not the same. I have some kind of perturbed evolution. Now, I would say that this is now not reversible because I apply some other Hamiltonians, but I would say this is also macro irreversible in a sense if I end up in two states that even under coarse grain measurements can be distinguished. So really macroscopically distinct things. So that if I have a magnet, then if I swap just one single atom in the magnet, this is macroscopically the same state. But if I really orient the magnet a little bit different, then I would say, that's a macroscopically different thing. So what you have here is that if this psi is within a first macroscopic state omega, then this is 1. And then I go forward and then go backwards and I look again at this omega, and maybe I will here have 0, because if I take this omega and this is outside of omega, well, then this will be 0, this will be 1. Then I will say this is irreversible because it didn't come to the same macroscopic thing. So I would define a process as macro-irreversible if there exists omega and some time that after this time, for all times, this is 1. So basically this is 1 and this is 0. That never comes back. Okay, and now this is something which I have, there is a QuantPH paper in 2015, it's a small exercise in which I took that this Hamiltonian that you are going backwards in time is the same as forwards with some perturbation. And I take extremely weak perturbation to be able to compute something. And then when you add this extremely weak perturbation, you come up with some expression where you have here a certain values of this perturbation in the basis of the old Hamiltonian. And now imagine that every time you run the experiment, this perturbation is different, because in no run you can really control it, and you cannot even control it to the sense that you repeat exactly the same perturbation. So you have some kind of random perturbation in every run of the experiment, and if you take the random distribution through the random matrix theory of these values, for example, some Gaussian value for this perturbation, you get something, the mean value over all perturbation over many runs have this exponentially decaying function, such that your mean measure of the macro irreversibility really goes towards 1. Because this was 1, this goes to 0 for the times larger than h bar divided by this distribution in perturbations. So for very long times you basically get something which is irreversible in the macroscopic sense. And so I would say maybe one can argue in a similar fashion that when you really have a detector, the reason why you cannot reverse this is that even with all your effort to reverse detection, whole detection evolution and procedure, is that you will not be able to control in full this process. And then necessarily, if you have some feature of your Hamiltonian of a detector, necessarily you will end up in something which is macroscopically distinct state from the state that you began with. So you start with photon here and detector prepared to detect. Photon goes to the detector, detector clicks, but now you want this state, this is my beginning state, to reverse, but I can't because of this irreversibility. Yes?
Imagine that you have not this problem of not really controlling your Hamiltonian.
Yes.
What would that mean, that the detector did click?
No, no, I really think in the previous state, comes in the previous state, this is this hyper kind of unstable equilibrium when it awaits of the photon to, when the photons enter the photodetector, there is this avalanche of the electrons, so you are in this stage of waiting for the avalanche of the detector and the photon is coming out. So I would really exactly the so This is of course the Gedanken experiment, but if there is any sense in assigning the state of the detector for somebody else outside who can control, what I mean is really coming back to the previous state, or at least macroscopically, maybe not a single atom, but really this awaiting for the detection of the photon. But what I want to say is that at the end, my question was, there are two different types of devices. One is the representative, one is a beam splitter, and the other one is a photodetector. And we call the photodetector a detection device, and beam splitter we don't call. And I think this is a physical question, and I believe that the key to understand the different features of them is irreversibility, in a sense of this macroscopic reversibility. The photon doesn't have this property of these perturbations. There is some property in the Hamiltonian itself of this device, and therefore is reversible, whereas the photodetector isn't. And that's why we call this photodetector. That's why it's useful in a sense. Now, with this I want to finish this first part of my talk, and I finish it with a possible dialogue. And a critic of this argumentation could argue in the following way. But your argumentation is only for all practical purposes, or FAP, to use Bell's acronym. No matter how low the probability is to reverse the evolution of the measurement process, it is still there. So how can the question of what exists be settled by an approximation? And in one of in a book by Schlosshauer, in the interviews, I paraphrase my answer from there. And I wrote something along these lines. Quantum theory cannot be both universal and not FAP. On the one hand, measurements must lead to irreversible facts, for otherwise no measurement would ever be conclusive. On the other hand, this irreversibility must be only FAP if quantum theory is in principle applicable to any system, including the measurement apparatus itself. The key point is that the subject can, of course, be described as an object, but then only as an object for another subject. And I would like to see more studies in the philosophy of physics explaining the fundamental nature of FAP, the philosophy of FAP, if you like, rather than regular attempts to expel this term from the foundations of physics on the basis of presupposed philosophical doctrine. So I use this opportunity to give the talk here exactly to say that, as a physicist. Okay, so let me now move to the second part, which is the Wigner's friend Gedanken experiment. And what the first part also suggests is indeed that the question of reversibility or irreversibility is, because it's for all practical purposes, the question of ability of the experimentator to control the devices and the systems. And therefore there is nothing as a physical cut between object and subject, but rather something what also Heisenberg was addressing is rather as a functional cut between subject and object. And this cut therefore can be shifted arbitrarily far in the direction of the observer, and this is what he wrote in an unpublished response to the EPR paper in 35, but you can actually find on the web this unpublished response. So what I really mean with this shifted is the following one example of the Wigner's friend. Here we see a system, there is a measurement device of the friend, and then there is a cut, a friend's cut between the system and measurement device. But it's not a physical cut, so it's not cut necessarily for everybody. So we can think about putting this observer in a box and the system, and then treating the measurement procedure by friend in a unitary fashion. That's, at least in principle, maybe possible, although we have not tested quantum theory to this extent. But nevertheless, all statements that we can make about the box are with respect to a new type of the detection devices, and these are detection devices of Wigner, who puts the cut then somewhere else. So in moving the cut, this friend's measurement instrument loses its function and becomes itself a quantum system for a Wigner. And this is an object that can be observed by a further set of Wigner measurement instruments. So I will take this as a working hypothesis for all my future statements. But of course, it could be that for example, collapse models are correct and that there is a one cut for everybody. Okay, so let us repeat the Wigner's Wigner's friend thought experiment. We have two observers, one of them performing measurement on a system, which I call friend, and after the measurement has been performed, the friend will apply the state update rule, whereas Wigner describes the entire process unitary. Now here it seems that there is a tension. Okay, there is a tension because the way of, and this will show in this next slide, the way how they will describe then the surrounding, if you apply the update rule or if you don't apply the update rule. The question is, what is the quantum state of the system? And I think the problem arises at that moment when you really think it's the state of the system to have some objective meaning, because this seems to be in tension or in contradiction, the two statements. More precisely, if you start with some system, let's say the system of a spin in x plus, so this is in z basis z plus plus z minus, and friend in some state 0, which is being ready to observe, not very importantly to describe in great detail, and this is a description given by Wigner, then after the measurement took place, usually in this consideration, Wigner ends up with writing an entangled state with a very specific phases here, which I choose one, but this should be governed by the knowledge of the whole initial state and the Hamiltonian between the system and the friend. And the Wigner writes this entangled state. Whereas friend, since he or she has seen the one or the other outcome, assign z plus or z minus to the system. And we see a certain tension between these two possible descriptions. I also want to say that the state that Wigner assigns, I will not consider this as an empty statement, but always operationally, I will request, and in all talk that follows now, that every state that I write down here has a way to be verified. Maybe not in a single shot, but maybe many runs, but there is a way to tomographically determine the state. So here I also assume that Wigner can verify this state assignment. So the state is for somebody. And this is, just to be careful, I request this strong notion of operational meaning of the states. We can verify this state assigning, by performing a certain measurement. For example, we can check whether this state is exactly this state or is an orthogonal subspace of that. And when we get in this measurement always the first outcome with certainty, after many repetitions, we can say, well, my state assignment is good, and we can repeat this same procedure. Now, Wigner can ask himself what actually friend sees, and what is the description of the friend. Now we can appeal on the usual situation in laboratory and say, well, friend sees one or the other outcome, because if I were in the laboratory and when I am in the laboratory, this happens all the time. It's obviously not always such an interesting situation, but I don't expect anything surprising to happen. But if you would like to have, as a Wigner, a little bit of more evidence, what actually friend sees, or whether she sees a definite outcome, you can actually use a slight variation of this experiment, which is due to David Deutsch, who proposed a friend to open the lab in a very subtle way, such that no information about the outcome whatsoever can leak out of the laboratory, but only the information I see a definite outcome. Okay, this is not very useful information, because out of this you cannot know which outcome has happened, but nevertheless you have some evidence that friend sees a definite outcome. You believe the friend, or you can even have programmed a machine that will tell you whenever there is a click in the laboratory, there is a message coming out, I see a definite outcome. But since this message doesn't contain any information about which of the two outcomes has been seen, it factors out of the state description by Wigner and doesn't destroy the coherence between the two amplitudes. So at the end of the day, Wigner has, I see a definite outcome from friend, and he can also perform additional measurements. Okay, so now this is interesting. So in that way, Wigner has a direct evidence that friend has observed a definite outcome. Maybe somebody will say, I don't need this. I believed from the very beginning that's true. That's fine as well. And also observe a definite outcome in his measurement. And now, on the basis of that, Wigner is tempted to conclude that the measurement arrangement, exactly this measurement arrangement, enables to assign joint probabilities for z and x. This is a non-trivial step, and I introduced this Deutsch version of experiment just to give you an evidence that, that on one hand, this is directly what I can observe, so I can certainly measure these probabilities, but I also have an evidence, also I don't know which outcome Franz is, that Franz has performed the z measurement, has seen a definite outcome. So in this early run of the experiment, both Franz seeing her outcome and me seeing my outcome. So it seems like this setup allows to measure them jointly.
The set of possible outcomes is common knowledge?
It's common knowledge. Wigner even knows that this is spin, that friend will measure along z direction, all this. They can agree upon. Okay, now I'll make the whole thing a little bit more complicated. Now I have towards Abel's theorem for Wigner's and friend. So I have a copy of the situation. So here I have a friend A and Wigner A, friend B and Wigner B. Friend A measure always along the z direction, just like friend B. And Wigner A and Wigner B could, for example, measure some additional observable that I denote as XA and XB. Now friends can, whenever they see an outcome, can send out these messages. I see a definite outcome. But as I said, this is not this really important message. It's only the message for Wigner's that not only the two of them see their outcomes, they are also aware that friends also see their outcomes and definite outcomes. So similarly like in the previous case, Wigner A, Wigner B attempted to conclude that all these values, Z A, X A, Z B, X B, are co-measurable, and one can assign joint probabilities. They attempted just because of that. Now, here is a statement, a very general statement on the standard Bell's test, when there is Alice and Bob and they perform some measurement and they choose between different measurement settings, ZA and XA Alice and Bob ZB and XB. It's known that if there exists a joint probability for all these four variables, then all Bell's inequalities are satisfied. And in particular, I will use this Clauser-Horn-Shimoni-Holt inequality that tells that this combination of probabilities, where this is the probability the two outcomes on ZA and ZB are the same and the two outcomes are different, it's a binary possibility, is more or equal to 3, and we know that in quantum mechanics, in principle, you can go beyond 3. Now, the question arises, are Bell inequalities satisfied in the Bell's test for Wigner's and friends that I introduced in the previous slide? Because I said the Wigner A and B attempted to assign the joint probabilities, and then there is this statement that if there is a joint probabilities, all Bell's inequalities have to be satisfied. Okay. Now the answer is the Bell inequalities will be violated. Okay, so in order now to make this statement, I want now very carefully to see what all enters in the derivation of Bell inequalities, what kind of assumptions. Then we will choose one state in which we will see that Bell inequalities are violated, and then we can look at assumptions, which of those are violated. Yes?
Just before we start doing this, but isn't it true that the knowledge that Frank has observed something, has observed a definite result, projects the big assignment, no. So it becomes a density matrix rather than a pure state?
This is the, sorry, I'm going forward and backwards.
Yeah, because if Wigner knows the state of possible if Wigner knows all possible outcomes and knows that one of those has been observed, he can have it's a classical probability distribution at that point.
No, I mean,
if he trusts that that friend.
I mean, this is one possibility that there is, but I would say that this is very similar to real collapse, because usually we say that this collapse, at the moment I get some information about that. I just got information that one of the outcomes had been observed.
So
there is nothing that couples. One of the outcomes is something which doesn't couple to this. So if you create an operator, one of the outcomes had.
yeah, but my state is just classical uncertainty over a state of possible outcomes that I fully know. So there's no reason why it would be a superposition rather than just an uncertainty. Ignorance, about a fundamentally really existing state. Do you see that? It's just ignorance about something that really exists.
That's exactly the point.
Okay.
To test what really exists. But at least I think if you assume that it's allowed to assign quantum states to objects of arbitrary complexity. I don't even need to say. It's allowed to assign objects to everything with respect to me, to my measurement apparatus. Then I apply to all what you have, to even your memory that actually memorized or get correlated with other two outcomes. So in the Wigner-Friend situation, you do assume that measurement has been performed by Wigner, nevertheless, Wigner described this as a huge entangled state.
Yeah.
And this piece of information, what I want to say that this piece of information doesn't make any difference to that, because this is a huge entangled state. I still control everything. And then there is a piece of information that doesn't.
But that information has to be in some quantum system. It has to be somewhere.
It could be. It could be. It could be
And that thing will
the easiest way is to have a three-level system. First level tells you its first outcome. Second level tells you it's the second outcome, and the third level tells you, or if you want the superposition of those, mixture of those, or the third level tells you it's a definite outcome.
Mm-hmm.
And if you send this third level, it will not correlate with this and will not destroy.
Oh, yeah.
So there are two I'm not sure what, so one is that it has to collapse because the friend has measured, and this is exactly what Wigner says. Let's assume that's not the case.
No, that's not the case. No.
Then you can always send the information about what's the weather outside, and this doesn't correlate. It doesn't mean that any information that's sending out of the box will actually collapse the thing, if this information is not relevant for the result.
Perhaps there is a simple way to say that. It's to say that Wigner, when he learned that his friend has a definite outcome, that's a measurement about an operator that has only two eigenvalues, and one of the two are the same for both.
For both of them.
And then when he learns that, either he learns that his friend did nothing.
Yes.
Okay, that's strange, but that's one possibility. And the other eigenvalue is linked to the degenerated state. And so when it's projected on a two-dimension space, which is the superposition. So it's not something that happens to give a reduction of the state.
Yeah, okay, so what you say, it's a nice thing. So if I understand that, maybe it's also three-level system, which is the first two is degenerative.
Yeah, absolutely.
And the third one is, let's say, I don't see a definite outcome. I don't know what it even means, but let's say we allow for this possibility, I don't see a definite outcome. And now this state will be correlated, both of those will be correlated with the same degenerative.
So you project on a two-dimensional space, and so you don't have something that is classical, but you keep the superposition.
Yeah, I agree with you, and it's also not decisive for this argument. Many people say I don't even need this. So this is absolutely, I understand that I see a definite outcome inside the box because it's not different than what I'm doing every day in my lab. Maybe there is a Wigner behind me, but I experience always definite outcomes. So for many people this is not really important, this part. But I like to introduce this because it gives some evidence for Wigner to start to think that he can, or the two of them can assign a definite joint probabilities for things. Okay, and okay, so I said that if it's really true that I can assign joint probabilities, then usually in Bell inequalities, we say then that all Bell inequalities are satisfied. And all what we measure here are just marginal coming out of these joint probabilities, and these marginals, by definition that the joint probability exists, satisfy Bell inequalities. So this could give an impression that maybe even in this case, Bell's inequalities will be satisfied. But now let's go to the assumptions, various assumptions that enter the derivation of these Bell's inequalities. So the first one is what I call universal validity of quantum theory, that the quantum predictions hold even if the measured system is large enough to contain itself an experimenter. So this is the idea that also the Wigner, that I in principle can assign a quantum state to the friend, to other experimenters. This doesn't mean that I assign a state to myself or to, they are still a cut, a functional cut, but everything what is on the other side of the cut, I can assign the quantum state, even if on the other side of the cut is a friend, another observer. Then there is something which I call independent facts. One can jointly assign truth values to the propositions about observed outcomes of different observers. It's technically the same as assigning this joint probability. Argument can be even made deterministic. I will not go into this is a technical detail, but one can really talk about assigning truth values where everything is probability 1. So this is the idea that both Wigner, that the truth values of the proposition of Wigner and of friend can be assigned simultaneously.
What's the difference between truth values and hidden variables?
Okay, so I'm talking here about really macroscopic, I'm here talking about directly observable propositions. For example, I hear the click in detector plus for Wigner, and for the friend I also hear the click minus in my laboratory. See, these are directly observable quantities.
Yes, but you cannot observe them at the same time.
Okay, but that's exactly the point. Okay, can we then observe? So, okay, so let's go back. This is a subtle difference, I think, between the usual Bell and this Bell version. In usual Bell, you really can choose to measure between one or the other. When you measure one, you don't measure the other.
Yes, sure.
Here you have certain evidences that they are in certain sense measured at the same time. Not by you as a Wigner, but there is an evidence that friend, and this is this message, the friend said, I actually measured Z. This message can even contain this. I measured Z and I saw a definite outcome. And then I measure something else on my side. At that moment, they are measured in certain... So I want to put now into contracts. I want to say something which I don't believe in. In the certain sense, they coexist. Not in the hand of one observer, but if you believe in some notion of objectivity that goes across the observers, then you say they coexist.
Okay, listen.
And now we will disprove this.
Yeah, sure.
Okay. Okay, so this is observer independent facts, and there is something which I call no disturbance, and that's you in the course of the Bell experiment, you don't measure disjoint probabilities. You don't know, but you can measure marginals. You measure only Z or only X. And Wigner will choose to measure only one or the other. When they choose to measure one or the other setting, they might something disturb in this probability distribution. They might even disturb on distance, like in a, I choose here the setting and this change the value of the truth values of the propositions on the other side. So this is a non-disturbance. The choices of measurement setting do not alter these truth values. And the last one is something which is very similar to every Bell inequality, is freedom of choice. The choices of measurements are statistically independent of the rest of the experiment.
So the observers are independent from each other in that sense?
The observers are independent from each other. Yeah, like in every Bell experiment. The choices of freedom, the choices of measurement settings are independent of each other. Now I want to tell you exactly the measurements that we'll perform. There are 4 possible measurement settings for the Bell experiment. The one is that what we discussed so far and gave rise to this assumption or hope that actually we can assign joint probabilities. This is the case when the friends measure Z, for example, spin over Z, and Wigner's measures the whole laboratories. And then they have some evidences that friends really perform the measurement of the Z component, the spin inside. But in a Bell experiment, for 2 Wigners, Wigner A and B, we have to choose between these settings. So we can choose XA, XB setting. Sometimes the first Wigner will measure ZA. What would this mean? Well, I open the lab and ask friend, what have you seen? That would be the measurement. And Wigner B does the same measurement, and then they have the opposite. The B will open the lab, and the last they will open the lab. Okay, so no disturbance is the idea that when I open the lab, I do not disturb the value. So this value, when I open the lab, the value that I will receive from Alice is exactly the value that can be read out from assignment of the joint probability. So I assume that there is a joint probability. So when I open the lab, I just marginalize this joint probability and I see what is this. So the assignment of the joint probability is the idea of observing independent facts, and no disturbance is the idea that when I open the lab, I marginalized these joint probabilities and read out only the Z. But it could be that by opening the lab, I change something on the other side, or I change the value here, or who knows what. I think this I have to assume. Okay, and then this is the idea of what kind of measurements I perform. And now let's pick up a very particular state. This is some state that this is a state of the 2 systems. They are entangled. Friends will be in the position of not yet doing anything, expecting to measure. Then when they measure the spin, they will get entangled. So at the end, you will have some entangled state of all 4 systems. I mean, system A, system B, and friend A and friend B. And there is some prefactor here in the state that was chosen exactly like that, such that at the end, what both Wigner and A and B measure are 2 possible observables. And this is asking the friends which outcome they have observed. These are Z observables and X observables measuring the labs. Without this, if you remember the CHS age inequality, they are a little bit shifted, these 2 sets of settings. So they are not always the same, but with this prefactor, we put that both Alice and Wigner A and Wigner B actually measure the same set of observers. This is a technical thing, it's not so interesting. At the end, really they can test the CHS age inequality, and they will see that they violate this by choosing between measuring the lab in this, entangled state, or by opening the lab and asking the friends. Okay, let us look at the assumptions and try to find out what are the possible way outs of this no-go theorem. So we can certainly put in question universal validity of quantum theory. That's what collapse models do, like Girardi, Rimini, Weber, or Dioschi, Penrose. the other possibility, the second one is the most interesting, so I'll skip this for now. As for example, some non-local theories like the Broglie-Borman mechanics, where you make even disturbance on distance by choosing different settings. And finally, you can have some super deterministic theories in which freedom of choice is denied, like in any Bell experiment. But there is a possibility that the really second one is violated. Then you cannot assume joint probabilities for two observers. And I think this is something which is in common of relative state or relational quantum mechanics of Carl Roveri, cubism, maybe some neo-Copenhagen way of looking, or many worlds interpretation as well, although it's very different than the first three of them. And if we insist on that, on impossibility of observing independent facts, I think one naive possible way would be to say, well, the facts of Wigner are more fundamental than of Friend, because he has superb instruments. But this has a problem of indefinite regression, because if we say Wigner 1 effects, then we can make nested Wigners and a more complicated Bell's experiment, in which will really deny then even Wigner will be now a friend of the Wigner 2, or Wigner 2 will be a friend of Wigner 3, and so on. So I think this has a problem of indefinite regression of observers, and therefore I think there is only two options. And one is in a spirit of many worlds interpretation, that you have some kind of wave function of the universe. It's not really very operational, and I don't think in this way when I do physics. The other one is that there are no facts of the world, or observer independent facts, but rather facts that are only relative to observer. And I think this is something which Chris Fuchs was mentioning many years ago in a reply to the referee comments that there's a relative to agents, I think they called at that time. But it's also implicitly in the relational interpretation. I also think that in Copenhagen interpretation you can still keep this view, and that it's a crude simplification of Copenhagen interpretation, assuming that implicitly there is a kind of a collapse in a very objective sense of the wave function within this interpretation. Of course, there are many facets of this interpretation, but I think this is still in line of the Heisenberg view that the cut is movable, and maybe that then we only can, depending where the cut is, then take one or the other facts with respect to one or the other agent or observer. And now, if time permits, I can go to the very last thing. That's a funny game that maybe even putting questions the idea of facts relative to observers. And because it has something to do with this, I was hesitating. I didn't really know what to do with this result for a while. I knew about this, but it didn't fit really in my understanding of the broader picture. But now I can tell you all my doubts, and also a small idea that allows one to actually prove that she or he is in a superposition. Okay? So even now, maybe, with respect to some Wigner description, maybe we are in the superposition. And the question arises whether there is any way to prove this or not. So here's the game. I think shows you that there is a way, operational way, that Friend finds out if she is in a superposition or not. Okay, so how? We again describe the usual Wigner-Friend situation, and to make it more dramatic, I consider a system that has actually the possible outcomes. This is just to make the discrepancy between two predictions that I will explain soon maximal possible. Okay? And so here Wigner describes the friend and the system. After the measurement takes place, again we have this entangled state from the Brukner point of view. And I take that there are D outcomes and D is very, very large. Now the friend doesn't know in which state she is. So this is really, we enter the laboratory and maybe there is a description of us from the Brukner's point of view, but we are not aware of that. We enter the laboratory, there is a system, I can measure the system, I can hear the click, but I don't know of any global description of the state.
So when you say in which state she is, means in which state assigned by Brukner?
In which state assigned by Brukner, she doesn't know. And I think this is a real physical situation that we enter. But what she knows, for example, the observed result, and let's say this result is K, one of those D results. Now, friend is told that Brukner will perform the measurement that will involve not only the system, but also the friend's memory at a later stage. And this measurement will have only two outcomes. One that will confirm the state in which they are, this entangled state, or opposite of that. Okay, so this is a measurement that is not disturbed for this state. You see, this is exactly the state in which friend and system are, from the Brukner's point of view, is an eigenstate of this measurement, of this measured observable. So friend sees the result and is told beforehand, there is a protocol, that soon after that, Brukner will perform a measurement in which the friend and system will be tested whether they are in this entangled state or not. But she doesn't know that she is in this entangled state. Okay? She just knows that this will be tested. Okay. Now, friend is required to send out her prediction to Brukner. Okay, so what friend can see, would do? The friend, she sees one particular outcome, I said K outcome, and because this measurement in the future will involve her also memory, she needs at least some way to predict this. So she needs to assign, that's maybe a problematic step, but she rather give some prediction, or maybe she will be killed if she doesn't give a prediction, so she has to do something. And I think it's meaningful for her to say that if I see a KR result, I can assign a state to myself, I see K, the Kth outcome. And then this is the state that I will assign to the situation in the lab. Like, this is the outcome, and this can represent everything, and detector, and my notebook, my memory, and everything. And I will look then what is the overlap with the state that will be measured afterwards. And this is this initial entangled state. So this K and CK is just one in all this superposition. And when I compute this overlap, this is 1 over D. Okay? And this tells you that almost with negligible probability 0 as D goes to infinity, this first outcome will happen. And then, therefore, I will, as a friend, she sends out the following prediction. The probability for the first outcome is almost 0, so it will almost with certainty be the second outcome. And what is important, this prediction is independently of the result that has been measured here. So no matter which result she observes, she can always send this same message. Therefore, this message will not disturb and destroy the coherence of the state inside, because it doesn't entangle to any of the outcomes, just like previous Deutsch example. Okay, and so friend sends her prediction, her prediction, and it's here, waiting here. Okay, now Brukner performs the measurement. And when Brukner performs the measurement, he sees the outcome 1 happening, outcome 2 not happening, because just confirming that the state is an eigenstate of the measured operator. And again, it's outcome 1, and again, it's outcome 1, and again, and again, and again, he can do it many, many times. At some point, Brukner stops, and there are two messages here weighting. One saying probability 1, first outcome happens with probability 1, and prediction by friend, the probability 1 is for the second outcome, not for the one. They are almost orthogonal. I mean, these are 1 to 0 opposite predictions. At some point, Wigner opens the box. Wigner opens the box, destroy the coherence, and friend will end up randomly in one of the results. Maybe will forget whatever she saw. This doesn't matter. It's only that they will share the same environment, that they can communicate finally. But what friend will see here is something which she made before as a prediction and what is actual result. And she sees the discrepancy. After a series of measurements, we collapses friend such that friend compare actual results with her previous prediction. And, sorry to see, okay, so she can then convince herself that something was wrong here in her prediction. And I think this is an evidence for her that she was actually in a superposition and that she had a false, I would say, I will say something more about that later, but that her prediction was based on the state that was in a certain sense wrong. And she can repeat this many times and convince herself that she better revise her prediction when she was in the black box. Therefore, not really believing 100% in what she sees, namely this result, but whenever there is a prediction to be done about the measurement that would involve her memory, she would rather be careful, not believing purely in the result that she sees in front of her, but thinking about the possibility that she might actually be in some entangled state as well. Therefore, the lesson from this is, if you want to say that there is a way to prove yourself that you're in the superposition, because there is an operational way that following the standard quantum mechanics and thinking only about all what's happening in my room, namely looking at all clicks and measurement records in my room, I might end up with a wrong prediction about measurements that involve my memory. Yes, please.
Well, you're doing something forbidden, which is, but you're probably going to tell us that you've done something forbidden, right?
Yeah, well,
no?
I don't know where it's forbidden.
You're using in one calculation on the previous slide an expression of the state relative to the friend. The friend knows that her state is K, times whatever. And the state relative to Wigner, which is psi.
Yes.
So you say, okay, she knows that somehow somebody tells her that Wigner will make this measurement, and then you say, I compute the product between these two states, and it tends to 0.
Mm-hmm.
But wait, what is this product between two states? Because the states are relative states, and this is one relative to her and the other relative to him. There is no way you can take a product of states that are relative to different observers.
All what I want to say is the following. It's better not, if your statement is, you better not do that, I agree. The thing is that she followed the textbook. And in textbooks there is written that if you observe an outcome, you should update your knowledge. That's the first thing. So she updated her knowledge. Then it was also said that if you want to have a probability for certain outcome to happen, you compute the overlap between two states. That's what she has done. So it's maybe something wrong here, but I want to say that this is very subtle. And the subtle is, maybe it's not subtle, but the message is, if your measurement, future measurement, will involve your memory, don't follow the textbook.
Well, it will involve yourself, yeah. Don't follow the textbook if you want. Or
don't follow, and there is no obvious. So now I want to resolve this later on, but there is no obvious reason what you should do. There is no obvious recite what should you follow, because you don't. You just follow. You see the outcome. You don't know in which state. There are many states, entangled state, that can lead to this.
Well, to go in the same direction than Alexei, I have two problems. I think the second one you will explain, because there is a way out of that.
There is a way out.
Namely, yes. If you take into account the fact that every measurement is relative and that you can talk about what somebody else thought.
Yes.
But that's part of the point we are going to do. But from for the first point, there is something that is I find strange, because following your reasoning, if you have a continuous observable of, for example, the position, then if you follow your reasoning, when you get one specific position,
yes,
you would conclude that it was not possible that before the state was a superposition, because the probability of getting one precise position is zero when you have a continuous spectrum of position. And that's not true. Even in ordinary quantum mechanics, you can have a superposition of position. Then when you make a measurement, you get one position. And of course, because that's a continuous spectrum, the probability for this result to occur is zero. But you don't conclude that because you got zero, that proves that your initial superposition was not the real state. And that's the kind of reasoning that you are going to do here.
No, I'm not sure.
Because imagine
that
the probability that your measurement give something could be zero when the dimensions goes to infinity. And of course, if you have a continuous spectrum, the probability that you get one specific result is zero. That doesn't prove that the initial state was not the superposition.
But first, here the conditional state is that I also already observed one outcome. So I'm not saying this outcome that a friend observed is zero. This is one outcome. From that outcome, I try to predict what will be the next outcome by Wigner. But in order to dismiss this continuity in 1-0, you can think about much more simple things, like there are two outcomes. All what I need is just that there is a difference between one prediction and the other. Whether this is 1 or 0, or it's 50% difference, doesn't matter, because repetition will conclude. So other possibility is that you have just two outcomes. Okay, you have just two outcomes as before, and for both of these outcomes, the overlap with the entangled state will be 1/2. So the friend will send out 1/2, 1/2, for example, here, for both outcomes, like if this is this entangled state or the opposite. But here will be always 1-0, 1-0. So there is always a difference between prediction based on from the outside, so to say, and the prediction from the inside. And there is a difference, and I want to say that friend can convince herself that it's better to use outside predictions, because she can come out and look at these two messages and see that this is correct one. So her prediction was not good because she took the view of the inside. But it's not wrong. It's just that you can convince yourself that you're in the superposition. That's a positive thing about that.
No, you can convince yourself after you've come out of the box,
yes,
that you had been treated by Wigner as being in a superposition. But
yes,
when you are still in the box, you cannot do that.
You cannot do that. Okay, so now here is alternative thing when you're in the box. Okay, in the box, you still, you have to have some belief in what is going outside, that there is some agreement of agents, that they do not fake each other, and also the outside could be a machine that you constructed before that. Franz can keep her prediction in the lab and stays there. So what was the prediction. The prediction was, given the results that you see in front of you, what will be the result of Wigner or a machine measuring the whole box, whether you are in the entangled state or not. And after a series of Wigner measurements, the list with the statistics is sent into the lab, and then friend can compare these two and see the discrepancy. So whenever the measurement involves the memory of the friend should not rely purely on what she sees in the box, but should accept suggestions also from outside of the box. And I think this is a resolution of the problems that I had. So I would like to conclude that Friend is likely to eventually update her state assignment, and this gives Friend sufficient evidence that her previous assignment should be revised. And for a while I thought that the idea of facts relative observers is maybe not tenable because of that, because suddenly at some moment I thought that there is differences between Friend and Wigner. Still there is no full symmetry, but this showed you somehow that Wigner has right and Friend not, as long as they concern only the results of the measurement in their respective laboratories, and Friend's laboratory is smaller than Wigner's laboratory, there is no problem. And I think we can keep going that all statements are relative statements. But then this example, for a while, appeared to me showing that when you make statements about something outside of the laboratory for the Friend, then there is obvious discrepancy between the two, and you should not give the same value to the relative state of Friend as to the relative state of Wigner, because even Friend can convince herself that her state assignment was wrong after repetition of many times of this experiment. But now I think the way out to keep the facts relative to observers is to allow Friend to have to get access to everything what is allowed. And in a way how in the last slide I showed that Wigner, for example, can send the state description as seen by him to Friend, and Friend can take this, the Friend in principle should include all the facts in her lab, but also facts in the Wigner's lab. There's nothing will change the state description, nothing will disturb or anything that the Friend will maybe lose the memory or something like that, if she has an access to both facts in her lab and the facts in Wigner lab. For example, she could know how the state is prepared, the Hamiltonian describing the measurement, and so on. So at the end, and that's what we suggest here, the Friend can learn the state of the lab as described by Wigner, as he can simply communicate it to her. And Friend is then entitled to use, if you want, two states. There's even more condensed and better way to phrase this. But for the example that I gave, the Friend can use actually two states. The state K, S, this is the state that is updated upon seeing the result in her laboratory, and the state is given by the Wigner. The first one will be used for any state, for any measurements that are performed within the lab, and it's surely this is the correct state. I mean, there is no doubt of that. But this is not correct state if you want to make the statements about measurements including Friend's memory and the whole laboratory. This is the state you should use. And then if you have an access to both, you will make both correct statements. And you still can keep that this is the relative description with respect to the Friend. I'm concluding now, and then you can ask. So there is several, I think, things that I'm omit here commenting on the very first, irreversibility. But I told about the no-go theorem, which says that it's impossible to jointly respect universal validity of quantum theory, the observer independent facts, no disturbance, and the freedom of choice assumption. And I think the lesson to learn about that is maybe that one of the possibilities to rethink and revise the notion of facts and talk about facts relative to observer. And then I try to argue that Wigner's friend is actually entitled to use both the outside and inside perspective, which resolve then the issues of this kind of paradox, the last one. And there is an operational way for an observer really to test if she's in a quantum superposition. With this, I would like to thank you for your attention.
Well, I have a question.
Yes, sure.
I have one question. Well, it's perhaps not a question, but perhaps a comment. I agree with 90% of what you say, but I have a disagreement on the last part, because I think that there is a way out to this paradox that is different from the way you presented.
Okay.
If you take seriously the idea that everything is relative to the observer, that's what I do in my interpretation, the convivial solipsism. And the term convivial means that you cannot have any discrepancy between what you observe and what you will hear Wigner say about you, or about the experiment that he does.
Mm-hmm.
In a way, that's sort of paradox, apparently. But if I'm the guy inside the laboratory, and if I see different results, then when I will ask Wigner what is the result of his experiment, I will hear that he found something that is compatible with my definite results. On the other side, if I am Wigner, probably I will see a superposition. But there is no way to compare the two, because if you take seriously the fact that everybody has his own description, then there is no way to have the real perception that the other had. So even if that is kind of meaningless, but even if you speak like that, Wigner has seen a superposition. When you ask him what he saw, you will hear him saying that he saw different results. Mm-hmm. And vice versa. Because there is no common way to compare different measurements. Each measurement is only reserved to the people which did the measurements. And you cannot compare what you perceived and what I perceived. So there is no way to get a discrepancy between us, because that doesn't mean anything even to say that I try to understand what you really perceived. Because what you perceived is nothing for me, because you are just a system, and you stay all the time superposed. But when I talk to you, I measure you. So I get one result, and this result has to be compatible with my previous results. So there is no way there is a discrepancy between us, but that doesn't mean that we thought the same thing.
Okay, so I think that I agree with 90% what you said, and actually that was my opinion from very recent. But then, I mean, maybe I even agree now. The purpose of the last part was not to communicate anything between Wigner and Friend, to avoid all this, but that Friend herself alone convinced herself that her prediction, based on all the facts that happened to her laboratory, which is the standard way how we do quantum theory, is actually wrong. Without communication, there is nothing like what Wigner sees and then I compare.
You have the list at the end.
No.
So the list is a communication. Because if you compare P1, 0, P2, 1, and 1,
so imagine
the second list is a communication.
Okay, imagine that I am a very skilled experimenter, and I can devise a setup that when I jump into, and I can, so I don't trust Wigner, I want to do it. So when I enter the black box, this device will check if I am in entangled state or not, in this entangled state or not. That's the device. I program this.
External device.
External device. I program this. Okay, I switch it on, I jump in the black box. Okay, then I just divide, okay, then I jump into the box and I perform the measure. And I see something, one of the results.
You will not see one.
No, wait a minute. no, I mean, I jump in the box and I perform the measurement of the spin. This.
Okay.
I'm sorry, I was not clear. So this, okay. So I make a device here, a robot.
So you replace Wigner by a device.
Yes.
Okay.
To avoid anything like communication, so this is the device that I program. I jump inside, I perform this measurement, and I get one result. And then I am asked to proceed in the protocol to give my prediction what will be the result of this, checking whether I'm in this state or not. Okay. Now, if I follow the textbook thing, which of course doesn't tell you anything what you should do if somebody will measure your memory, but that's where we should extend the textbook. Then you say, this is I saw this result, I project on this result. I do a non-trivial thing, maybe there is other ways, but that's most obvious. I do a non-trivial thing and say, when I have this, I will assign to my memory, I saw this result. Now I have to make the prediction about the result outside that I program. Then I don't rely, I don't communicate anything. I send out this thing, I send it out, and well, the machine does, and make it many measurements, never disturbing this, because this is an eigenstate of the measurement observable, doing that. There's no communication. Still, at some point I open the box. And I forgot what I've seen. Then there are these two things that are compared just by me, not by Wigner and me, and comparing this. I change my perspective, I understand. I jump into the Wigner's perspective.
You will not get that. If you do that,
I will not get these results.
According to really taking into account the fact that all is relative to you, if you do that, replacing Wigner by any device doesn't change anything.
So what
this device for you, which has performed measurements on the whole of the laboratory, your memories and so on, this device is, before you have a look at it, is in a stable state for you. Then, when you have a look at it, it's exactly the same situation than talking to Wigner. You make a measurement on Wigner, or you make a measurement on this device. And then, just before this device was in superposition, and when you will look at it, you reduce this device because you perform a measurement on it. And then what you get is totally compatible with the previous result that you got before. So you will see two and not one.
So you,
if you do this experience,
you say that you will see here two.
Yeah, absolutely. You won't see one. There is no reason, because
I don't understand this.
Because well, there are
do you
reasons.
think that the Wigner will see one?
No.
Not even the Wigner.
No. I say that doesn't mean anything to speak from my point of view of what Wigner really saw. I have not the right to do that.
But
what I can say,
here's the device that avoids this and forces you to come into the situation to make statements in comparison on the same, if you want, space-time point. These two predictions are next to each other and they are contradictory to each other.
And in this case, I will predict that Wigner, when I talk to him, will say that he saw two and not one. And that's coherent with the fact that I assume that everything is relative to me, because there is no absolute fact. When you do that, you mix a sort of relative presentation and absolute one, because you assume the fact that what Wigner saw is something there which is available for Wigner and for his friend. If you say that there is nothing absolute, then even what is written somewhere is not absolute.
I also, okay, this is very, okay, so I think then you will have to revise the way how we compute quantum probabilities, I mean, in my view. I mean, we have to give a prescription how this will change now from 1 to 2. But let me say that I don't think that there is an absolute thing. Previously, I thought about, and I'm still seeking for this description, I didn't give up, that there is absolute equivalence between all descriptions of each observer. It seems to be not trivial, even if this is possible. Okay, and the reason is, and I don't think it's unreasonable, we did give here Wigner a little bit more power than Friend. A little bit more power. Like he can, because Wigner sees unitary description for what Friend does. So there is some asymmetry already here, although I think that overall, each all relative descriptions are equivalent. In this particular case, it seems to me, there is a slight asymmetry already introduced. Now, I'm not saying that Wigner has the absolute, because there is a Wigner 1, 2, 3, 4, but I think that you still save the relative state by giving everything what is available for one or the other. Wigner, you cannot give the result, Wigner, because this will destroy the thing. But Friend can know this state given by Friend. There's nothing wrong, and can help Friend to make statements about the future. This is also part of the relative state.
A short question. It's about the conception of measurement that was developed by Peter Mittelstadt. He very much insisted not upon the inclusion or exclusion of the subject, of the experimenter, in the field of the description of quantum theory, but on the possibility of distinguishing between the theory itself and its meta-theory, namely the set of presuppositions that allow one to elaborate propositions that can be said to be theoretical propositions. Now, precisely when you think of your first, the first proposition of your set of 4 statements, namely universal validity, you say quantum prediction holds even if systems includes the experimenter. Here, I think Mittelstadt would distinguish between 2 points. Either the quantum description includes the experimenter as an object, or it includes the meta-theoretical presuppositions of the experimenter. But the second possibility is definitely excluded, because the theory cannot be mixed up with its meta-theory. So can you, maybe, don't you think that in this case, the first proposition, namely universal validity, should be restated this way, namely quantum prediction holds even if system includes the meta-theoretical presuppositions of the experimenter. And in that case, it would be obvious that it would be ruled out.
So I'm not familiar with all what you said. So the idea is here that not the theory should include the experimenter that does this measurement, because the distinction between subject and object has to be preserved, but it can include other observers that perform maybe their measurements. But for my measurement, I'm still outside. I still don't apply quantum theory of myself as an observer, but I can apply to other observers. Does this answer to
a certain extent?
So I think that there is a necessity to have the observer outside of the quantum mechanical description, but each observer can request this for herself, himself, not for the others. The others could be part of the systems.
Thank you.
You made the statement, so you support the statement that facts are relative to observers, and you say that this statement is assumed by several interpretations, such as Cubism and Neo-Copenhagen interpretation. But don't you think that the statement "facts are relative to observer" could be made more precise to explain more precisely your point of view? Because we could consider that the facts are relative to real observers who actually see the outcomes, or we could also say that the facts are relative to possible observers, and in this case relative to rather to the measurement settings, and I will guess that in the first case it's more closer to Chris Fuchs' point of view, and the second one to
I have not made my mind about that, but let's say that I don't necessarily require that there are real observers present, but I think I will be pleased if there is relative to environment in which information of the result is redundantly imprinted. So that means if I have no Wigner there, but there is a machine that upon the click of the detector will write down something, I would be pleased with this, I guess. After all, maybe a friend will come out and see what is imprinted. Of course, the cubist will say, well, there is no meaning to assume that there was anything until somebody come out. But I don't, this is a nice exercise. I don't see what advantage of the one or the other is. So I guess I will take a kind of also a view that as long as this is imprinted in the environment redundantly, irreversibly for all practical purposes, I will call them this is relative to this environment. I don't know what's the best word, but I guess in this environment then observers can communicate and agree intersubjectively that there is an outcome, an effect, and they will be all fine. But then on the other level of Wigner's type of observers, you can have those that can communicate, or they are not maybe present, but they are machines. And I guess not necessarily what I will. At least more about what quantum state is in general. Is it there when there is no agents or not? But in any case, we should not think about something very objectively, because there are these different levels, and we cannot assume coexistence of the facts at these different levels, different environments, or maybe different agents if you take the other option.
Okay, so two small points. One is very much like Michel, I was thinking about Mittelstadt during the last part of your talk. So Mittelstadt worked a little bit with this young man at the time who was also Guido Bacigalupe's friend, who then kind of left science, but he became a professor, I think, in Switzerland, called Thomas Breuer. Thomas Breuer proved a theorem that Mittelstadt has in his book, that every self-referential theory must be incomplete. So I think you're discovering the same thing in a different language.
No, I don't think so.
Oh, well, okay. So,
no, I know this
so
work,
what you're,
yeah.
So I think what you're discovering, is my impression at least, so very welcome to comment on that, is that if she's talking about, if she's considering states that relate to herself, to her memory, that is self-reference. And that's where we see that this cannot be complete. So, as you say, it has to include something from the outside, because otherwise it's not complete. So I think that this is an instance of Breuer theorem that you've discovered through a different argument. So that was my first point, maybe, I don't know, yeah. Okay, so that's the point. Maybe.
Okay, so I was thinking you're
that.
still addressed to the axiom. That's why I reacted. I don't think so, but I'm closer to what you're saying now. In the axiom, one is not self-referent because you exactly axiom one, which is not maybe nicely formulated and precise, is the statement that you should not include yourself, but you include everything outside. You can assign.
But whenever she gets psi, and psi includes herself, and she starts working with psi,
okay,
that becomes self-referential at that
this
point.
becomes self-referential, but the axiom, the postulate for the derivation of Bell inequality is not one, which is called universality of quantum mechanics, does not assume that you should assign state to yourself.
Yeah, I didn't say that.
I didn't say that, but I'm addressing this. This is not. It says it can include experimentator, but not you. All others, like Wigner can have a description of the friend, but not of himself. Now about this. This is maybe, this has some problem in self-referentiality, but there is a non-trivial part of that. As long as you talk about states the states of the systems, and maybe you seeing these states of the systems, there should be no problem.
No, there shouldn't be a problem. No.
As long as you don't talk about
yourself as a system,
you can. But for example, you can, for example, think about the spin has up and I see up. What is the probability that later on the spin will be x and I will be seeing spin x? This doesn't have a problem. But there is no problem to add this. This we usually say also in classical physics. Many times we talk also about our memories and what we will maybe see or memorize in the next moment, or giving predictions. It's only really when you include entangled state, like the Wigner, and then there is a problem. But I don't know whether there is a problem, because you should take Wigner's point of view of when you make statements, even if you won't make statements about measurement on yourself. And there is an operational way that you can do this. This is what something was not clear to me, never. Because I was thinking, like, if I make statements about future measurement on my memory, and then I lose my memory because this measurement is disturbed and so on, I will not be able even to compare this. There is no meaning in this exercise. But now I see that there is, maybe in restricted class, a meaning to this. That's the way how you can check statements about future measurements on your memory. This is not the most general thing and so on. And in many cases, maybe it doesn't work. But in this special case, it works because the measurement that you perform on your memory is not disturbing your memory. And therefore, you can make at the same time your predictions without ever disturbing anything on state. Wigner can make measurement because you're in an eigenstate of this, you don't disturb. So you can make this statement that corresponds to the same physical situation, and then in order to compare this, you may make some destroy. But these are the documents that are there. So I think that there has something to do with making statements about your memory. But it's not a problem, at least in this case. You should just adopt Wigner's, because this is the way.
Which is what Broy's theorem says. You should go out of.
You should go out.
Okay, so that's what you're saying in different words.
Yeah. Okay. Yeah. This is the same. Yeah.
Okay, that was my first point, but maybe a second later or now, as you want.
We'll have to come back, but let's
okay. Second point. Okay. Second point is. Actually, to go back to the first part of your talk, when you were talking about irreversibility, I was glad to hear that, because of course, once you characterize measurement through irreversibility, you can talk about entropies. Mm-hmm. So once you have irreversibility, you have entropy increase.
Yes.
In that sense, I would like to go back to the question I've raised during the talk, is that, okay, so she sends information, I've observed something. Mm-hmm. If she has really observed something, there is entropy increase because there's been a measurement there, right? So, so even the state seen by Wigner must change, because physically the entropy of this whole thing has changed.
Not for Wigner, it's unitary. It's entropy
Well,
conservative.
yes, but I don't like situations when there is entropy production inside, and somehow you say it's all unitary, even with the window open. If the window had been closed, if there had been no information, yeah, but there is entropy production in that box, and the window is open, and you cannot keep it. You cannot keep that entropy just inside, you know, because otherwise you have to have a horizon there. If you have a horizon that sort of prevents this from going out, but once your system is open, you can only have a horizon, otherwise entropy should be the same out there.
First, as I have said in the past, it's not open. It's not important to open it. If you want to start with, let's assume that these outcomes coexist, assign joint probability, you end up with a no-go theory. It was just to, Wigner has a little bit of evidence. This is my batteries, but I can switch it on again. So it was just to have an additional kind of argument in supporting the view that there are joint probabilities. But imagine there is this box. And there is a lot of things that friend can talk about. What is the weather, what she had for lunch yesterday. And this is all in one corner of the box. This all factors out from all others. So if you want to, you start with a pure state, then you, from the Wigner's point of view, you end up with a pure state where you have a product of two subsystems. One is a lot of things that contain information about outcome, and then in this corner, there are a lot of things that contain no information about outcome. Their factor is out, weather, lunch, and that a definite outcome has been observed. This you can chuck, send to out and send out to Wigner and close again. This doesn't change anything about the description of the entire about the outcomes.
That's not correct. No. No, of course. No, because again, in terms of entropy, if you think about it, forget pure states. Think about it in terms of entropies. There has been entropy production, and you have an open system. Something.
Entropy production you only have if you want to erase information. Maybe at some point.
No, that's why I insist. You've talked about an irreversible process. This is why there is entropy production. Now there is no. Yeah.
No. The first part was where, under which condition friend will say that the measurement has happened, or any other observer within its laboratory. This is the first part.
Sure.
But then the core of the Wigner is, if you insist on that, if you take this, and I don't know how will you come out. I mean, really, I think that if you don't accept this, there is something you think from one of the other reasons that the breakdown of superposition. The game of the Wigner is that there is another description of the same process, which is entropy production process for the guy inside, that is unitary. And this is also not an empty statement, because I request that every state is written down, also the Wigner state of a unitary measurement process of friend can be tested in an experiment with a measurement device that will also produce entropy, but for Wigner, not for the friend. So entropy, no contradiction.
When you open the window, entropy is not for somebody. There is, as long as the window is open, Wigner is supposed that entropy production is not inside your universe, unless you have a horizon there.
No, when you open and you send a pure, when you send a pure state, it's a pure state. There's no entropy. If you have two product states and you send one
maybe talk
product
about
state,
it later, but
there's no entropy production.
Perhaps just before stopping, well, I would like to continue the discussion about the relative point of view, but I have one different question. You say that you compare cubism, relative state, and neo-Copernicanism. It seems to me that if you are really, if you follow really the textbook, then you have a really easy solution, which is not satisfying, but which is just to say that as the friend has made measurements inside the box, everything has collapsed, and that's it. And that's what every follower of usual textbook would say. There is no problem because the measurement by the friend has collapsed everything, So Wigner outside should know that it is collapsing and that he doesn't have to use the proposition. But that's the Copenhagen point of view. So what is for you what you call the neo-Copenhagen point of view?
I think there is an for this you need to adapt the measurement posture. Say, when measurement takes place for an observer, then it should be projected for the observer.
I agree with that. but this is not the usual Copenhagen point of view.
Yeah, okay.
Because Copenhagen has an objective presentation. When a collapse occurs somewhere, it occurs for everybody, not just for the people having made
cannot comment. Yeah, this is
the
majority of people understand like that, and I think it's not compatible with the quote by
agree.
Heisenberg.
Okay,
And I think it's more Bohr. Bohr would say that every physical situation, this is paraphrasing, every physical situation automatically induce kind of a cut.
Yeah.
So you look at the physical situation, whatever it means, and then you know where the cut is. And then Heisenberg also comments in this paper, which is applied to EPR, on the difference between him and Bohr, where Heisenberg is really kind of insisting that it can be shifted everywhere towards the observer.
And Heisenberg is able to move it.
To move it. And then if you are able to move it, there is no collapse for everybody. I mean, that.
So it's possible to okay.
So I think that maybe they were not consistent, or he was not really of the same opinion.
That's an historical point of problem, of course. But of course, I agree that this is not a good solution. But I would really like to go on.
But it's interesting that the collapse, like if there are people who do not believe in objective collapse, but they will argue in a similar what you say, and they are in the old school Copenhagen, that as soon as information is available somewhere, let's say in the memory of friend, it should collapse. So they are not saying that it's because the mass has increased and collapse is induced by gravitation or whatever. No, it's even information theoretical approach. But as soon as this information is available somewhere,
but including the fact that it is printed somewhere, with nobody having seen. But it is printed by a computer. And that's available, so the collapse has occurred.
Yes.
And that's problematic, of course.
That's problematic, of course. I agree. I mean, not for everybody.
Not for everybody.
For those that are next to that.
Okay, so we have to start. But thank you very much, Caslav.